All right, we're going to be looking at how to combine and transform power series. These are going to be material from section 11.2 of the book. I wrote 10.2, but it's 11.2 of the book. Um, it was discussed under power series, but I feel like it's better for us to come back to this after having discussed Taylor series. So if you assume that we have an interval I and the center of the interval is A, and on this interval, ck x to the k is a Taylor series for the function f of x, and dk x to the k is a Taylor series for g of x, then the following results are true. That ck plus dk x to the k is a Taylor series for f of x plus g of x. Okay. All the convergence properties that come with ck and dk applies, and then ck, or let's do ck ck x to the power of k plus m is the Taylor series for x to the power of m f of x. And ck x to the m to the power of k is the Taylor series for f of x to the power of m. And I'm just restricting my statement here to the Taylor series because we've extensively dealt with the Taylor series, but the word Taylor can easily be replaced by the word power. So because this applies to all power series. All right. Okay. So I was underlining, so I might as well underline everything to just show you that we could replace all this with the word power instead of Taylor. All right, so we're not going to prove this theorem because that's beyond the scope of our course, even though it's quite easy to prove. Let's do some examples. So we want to find the Maclaurin series, which is the Taylor series centered at x equals 0. So the Maclaurin series for each function for f of x. So for f of x. In this case, the first one, f of x is equal to e to the power of negative 2x. All right. So to do this, we just have to recall that the Maclaurin series for e to the x is summation k from 0 to infinity x to the power of k over k factorial, which is 1 plus x squared over 2 plus x cubed over 3 factorial, etc. We did this in class, and this is valid for x between negative infinity to infinity. Converges for every x if we are able to if we're able to get the whole every term of the series. Okay, so we're just going to use part we're just going to use part 2 of our theorem. All right, so part 3, let's see. Well, thus e to the negative 2x is just going to be summation k from 0 to infinity of negative 2x to the power of k over k factorial. Okay. All right. So, what does this mean? This means we have 1 plus negative 2x to the power of, well, no power yet, per power of 1, and then minus 2x squared over 2 plus negative 2x to the power of 3 over 3 factorial, etc. All right, this doesn't fit neatly into one of the groups of the things we mentioned in our theorem, but the fact that that negative 2x is just, negative 2 is a constant, so that allows us to use this part of the theorem that just says if we have x to the power of m, we can replace x with x to the power of m. So we can just think of negative 2, keep the constant where it is, and think of negative x as x to the power of m. All right, so we just end up with 1 minus 2x plus 2x squared minus 4 over 3x cubed plus etc. Okay, and you can show that the interval of convergence here is actually negative infinity to infinity. So you should show this. You should probably show this. You can show it using the ratio test. All right. Well, let's do another example. Well, let's still work with exponential function. So this is e to the negative x squared in this case. Okay. So we're just going to be replacing x with x squared in the series, the Taylor series or the Maclaurin series for e to the x. So again, let's recall that the Maclaurin series for e to the x is k from 0 to infinity of x to the power of k over k factorial. And again, this is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. So that e to the negative x squared is going to be summation k from 0 to infinity of, you just substitute negative x squared for x over k factorial. So this is going to be 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial, etc. Again, the interval of convergence of this is negative infinity to infinity, and you should try and show this. All right. Now, how about if we want the Taylor series for f of x? We want x squared e to the x. X squared e to the x. Again, we know that the Taylor series for e to the x, the Maclaurin series, is that. So we're just going to end up with x squared e to the x is just going to be x squared summation x squared times the Taylor series, the Maclaurin series for e to the x, which is going to be summation k from 0 to infinity. X squared has no k, so we can just bring it inside, and this ends up being x squared times x to the power of k over k factorial, which is the same thing as summation k from 0 to infinity x to the power of k plus 2 over k factorial. And if you want to expand this, this will look like x squared over just x squared to begin with. When k is 0, you have x squared. When k is 1, you have x cubed over 1 factorial, so x cubed. When k is 3, you have 2, you have x to the 4th over 2 factorial, x to the 5th over 3 factorial, etc. Okay. So in this third example, we made use of the second part of our theorem here, for our result here. So e to the x was f of x, and x to the m, x squared was x to the m, and we just ended up having this this representation for the Taylor series. Okay. Now we're going to switch gears and see how we can use one Taylor series to get another Taylor series by integration and differentiation. What do I mean? So let's say differentiation and integration of Taylor series. Again, this can apply to any power series at all. You can integrate and differentiate any power series, but when you do that, you have to recheck the interval of convergence. All right. So we're going to do examples. We're going to use differentiation or integration to find the power series of each function. All right. Okay, so the first one is f of x is x, 1 minus x to the power of negative 2. Okay. Now, this requires some observation, and let's observe it. So observe that when we take the derivative of 1 over 1 minus x, we end up with x, 1 minus x, to the power of negative 2. I think, well, let's do it using chain rule. So this is like the derivative d dx of x 1 minus x to the power of negative 1. So if you take the derivative, you bring it down the negative 1, and then you multiply, you subtract the exponent by 1 minus x to the power of negative 2, and you multiply by the derivative of the inside. So this becomes 1 minus x to the power of negative 2. So we have this 1 minus x to the power of negative 2, and then we also found that the derivative of 1 over 1 minus x is 1 minus x to the power of negative 2. Okay. But there are a few things we know, or there's one thing in particular we know. We know that the Maclaurin series for 1 minus x, 1 over 1 minus x is summation x to the power of k from 0 to infinity. And this is valid for x, absolute value of x less than 1. So if you go back to your notes from section 11.3, you will see this. Look for where I listed about 5 to 6 power series. Okay, and you can even think of this as a geometric series where r is 1, a is 1 and r is x, and this is gonna converge, and when it converges, its sum is 1 over 1 minus, its sum is going to be a over 1 minus r. In this case is 1 over 1 minus r. Okay, 1 over 1 minus x, I mean. And this converges when x, in this case the ratio, is less than 1. When the ratio, in this case x, is less than between -1 and 1. Okay. So I felt like I just rambled a whole lot, like in the past 1 minute. All right, so that means that our 1 minus x to the power of -2 is going to be the derivative of this series, x to the power of k. So it's going to be the derivative d dx of 1 plus x squared plus x cubed and so forth for x 1 less than 1, and this is going to be 1 plus 2x plus 3x squared plus 4x cubed and so forth. So we've managed to get the series representation for 1 minus x to the power of -2 as k from 0 to infinity of k plus 1 x to the power of k. Why k plus 1? When x is 0, we have 1. That's 0 plus 1. When x is 1, we have 2. That's 1 plus 1. This is 2 plus 1, etc. So that's why we have k plus 1. I want you to find the interval of convergence. Okay. All right, so the next one I want us to look at is, how about if f of x is minus natural log of 1 minus x? We want to find the power series presentation. In this case, it's just the Maclaurin series. So again, we have to start with an observation. The observation is that minus natural log of 1 minus x is the integral of 1 minus 1 minus x, 1 over 1 minus x. Okay. So if you do this integral, if you perform this integral over here, this is what you're going to get. Maybe plus c, plus some c. Okay. So maybe we have to put our plus c there. Plus c. Okay. All right, so we already know this means the natural log of the absolute value of 1 minus x plus some c is going to be the integral of 1 plus x squared dot plus x cubed dx, okay, which is equal to x plus x squared over 2 plus x cubed over 3 plus x to the fourth over 4, all right, plus dot 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 plus some c, okay. So if we maybe we take all the c's and just bring this c over here, and bring this c, take this c over here. Let's call this c1, and this is c2. Let's combine both of them on one side and call it c. So this is x plus x squared over 2 plus x cubed over 3 plus x to the fourth over 4, and then plus some c. All right, so this means that oh, you know what, let's keep our c over here. Let's keep c2 where it is. Let's bring it to where c1 is. So let's call it c. So this is c1 and this is c2, right? So sorry, let's take all this, bring this. Okay, so we combine c1 and c2, so kind of c1 minus c2 is called c now. But in our original expression, in our original problem, that means that c is 0. So if c is 0, we get that minus natural log of 1 minus x is going to be summation k from 1 to infinity x to the power of k over k. So that's what we have. This is x to the power of 1 over 1, x to the power of 2 over 2, x to the power of 3 over 3, and so forth. So this is our series representation of the function minus natural log of 1 minus x. And we're able to do this because we know the representation, we know the Maclaurin representation of 1 minus 1 over x, right? 1 over 1 over x. So that from knowing the series for 1 over 1 minus x, we're able to get the series for 1 minus x to the power of negative 2. We're also able to get the series representation for minus natural log of 1 minus x. I hope this is making sense. Okay, now there is one I want you to think of. The one I want you to think of, let's call it number 3, is the representation for for inverse tangent of x. Okay, so I'm going to start it off for you. I'm going to give you a hint. So if you observe that the inverse tangent of x is the integral of 1 over let's see. What is the derivative of the inverse tangent of x? All right, so let's begin by finding the derivative. So observe the inverse tangent of x, the derivative, its derivative d dx of the inverse tangent of x is 1 over 1 plus x squared. I agree with that. Now, this means that inverse tangent of x, maybe plus c, is the integral of 1 over 1 plus x squared. Okay? Now, one other thing I want to show you is you can write this as the integral of 1 over 1 minus negative x squared. Okay? Now, so my hint for you is to use the representation, the series representation of 1 over 1 minus x. But instead of this x, instead of using x there, you now represent it. You now replace it with negative x squared, and then simplify it as a series, as a summation, and then take its integral. Okay, all right? So I want you to think about this. This is for you. We're going to talk about it in class. Or I may give it to you as a quiz. Hint, hint. All right.